welcome. We are Group 5 of Interdisciplinary Mechanical Engineering Design. For our project for this course, we're working on improving current gravity foam heat exchangers to get a higher heat transfer coefficient and a higher heat transfer. Gravity foam heat exchangers are a type of heat exchanger that uses the heat from current systems that are using hot water and transfers that heat to the cold water coming in from the city or from your well. It does this by having the hot drain water going down a drain line pipe with the cold water from the city and several smaller pipes that twist around the drain line. This allows for the heat of the drain water to transfer from that water to the cold water. This allows there to be preheating of the city water so that there is less energy required by the water heater and fuel savings.
Current gravity foam heat exchangers are getting between 30 and 40% effectiveness, usually. Our goal is to try and surpass that. We're aiming for 50% effectiveness. The designs we've chosen to try and achieve this are using a swirler, which will project the water onto the sides of the heat exchanger to create the film of the water. And we've also opted for a spring, which will be inserted into the heat exchanger and will cause a splashing effect, creating more turbulence, which will increase the heat transfer of the water.
The beginning of our process was the design proposal stage. During this stage, we researched different concepts that we could incorporate into our heat exchanger in order to increase overall effectiveness. Some of these ideas were later improved upon while others were rejected. An example of an idea that was improved upon was the Archimedes screw. The concept of the Archimedes screw was to create a vortex in the drain pipe, which would increase effectiveness of the heat exchanger. However, we realized the concept would not work due to destroying the water film. This idea was later improved upon into a spring. The spring can induce turbulence in the drain pipe while keeping the water film intact. An example of an idea that was rejected was adding surface roughness to the inside of the drain pipe. This idea was rejected due to the high cost of manufacturing as well as causing permanent damage to the heat exchanger.
For our conceptual design, we found that in order to increase the heat transfer coefficient, we needed to increase the turbulence of the flow and to maintain the film flow down the hot water pipe. The designs that we came up with were to increase the surface roughness of the drain pipe and to add a spring to the drain pipe to increase the turbulence inside the drain pipe. And also, we designed and installed a swirler to the drain pipe to direct the flow of the hot water tangentially down the drain pipe to increase the contact time between the hot water and the cold water of the heat exchanger.
So using MATLAB, we did a simulation to find the overall heat transfer coefficient of our system with the spring and without the spring. We also changed the hot water flow rate at different speeds to see how this changed the heat transfer coefficient. We did this by first using relationships with Reynolds number, Prandtl number, and Nussbaum number to find the convection heat transfer coefficient. Using this, we were able to find the overall heat transfer coefficient and determine that it would be higher when a spring is used and at higher flow rates.
The CFD simulation for this project emphasized flow across the swirler, and of importance was pressure drop, as the higher your pressure drop, the lower your velocity. And in this drain, the velocity can only be as low as 0.6 meters per second before it starts to get clogged. In our simulation, we found through these velocity vector plots here that the flow was consistently above 0.6 meters per second on all the swirler blades. And these blades were the main area of concern, considering the roughness of 3D printed plastic. Since these blades are rough and roughness increases pressure drop, a finer mesh was used in this critical area to get more accuracy in the simulation.
In addition to all the other simulations that we've done, we also needed to do an energy and cost analysis. For this energy analysis, I had to make a few assumptions. The first assumption that I needed to make was what the heat transfer coefficient was for current heat exchangers. I assumed that this would be 35%. I also assumed that we would be having a 50% heat transfer coefficient for our improved gravity-film heat exchanger. I also had to assume that the flow rate for the hot water loop would be 2 gallons per minute, with the temperature at the inlet as 35 degrees Celsius. The cold water loop would then have a flow rate of 1.2 gallons per minute, with the city water initially at 10 degrees Celsius. Finally, I assumed that the average household would consume 60 gallons per day and that the lifetime of the gravity film heat exchanger is equal to 10 years. After doing all the energy analysis, we found that the cost savings was that of $32 yearly for our gravity film heat exchanger versus current ones. I also found that over the 10-year lifetime period, it would be around $314 of savings.
The first step that we took for our detailed design was to create a layout drawing of our current system with respect to the existing gravity film heat exchanger. This allowed us to see where all the systems would go. The layout drawing allows us to see where we'll be placing items such as valves and thermocouples with respect to the existing system. The next step we took was to draw items such as the heat exchanger, valves, and hose fittings onto SolidWorks. We then took these parts and made an assembly drawing to see what the final system would look like. Finally, using both the layout drawing as well as the assembly drawing, we were able to build our system in the lab. We also created a bill of materials to keep track of the cost of each part in order to keep the cost of our project to a minimum.
Bo helped me design the swirler. He researched the specs for a Kaplan turbine, and I designed it based on that. These angles, as you can see, this is a 45-degree angle, this is a 15-degree angle, and this bank is a 20-degree angle with 5 blades, just as in the typical Kaplan turbine. These holes that you can see here are where sticks will be inserted to actually have it sit in the heat exchanger. We also cut a 1-inch diameter PVC pipe and put it in here just so that we could limit the amount of 3D plastic we needed to use. And we would continue to drill holes through that afterwards. After a lot of input from the professor, the design was finalized and I modeled it on SolidWorks before 3D printing it.
For the spring, we first made an attempt to create a spring out of copper wire. We chose copper wire because copper is the most widely used material in piping. But copper seemed to be too soft of a material to be made into a spring, as it cannot keep a constant pitch throughout. So we had to use a different material for our second attempt. For our second attempt, we decided to make the spring out of music wire. We chose to make it using music wire because of its high elasticity. The problem we encountered with music wire is the installation of the spring in the heat exchanger because the spring cannot be heat treated. It cannot keep its helical shape. Therefore, we had to keep the spring on the mandrel, clamping the ends as to keep its shape, and then releasing it in the heat exchanger. But then the removal of the mandrel has become a problem since the space in between the mandrel and the spring is too tight to be reached by our hands or like pliers. So for our third and last attempt, we opted on buying a pre-made spring of 2.9-inch outer diameter and 5-inch in length. We bought five of those springs and welded them together to match the length that we require for our heat exchanger.
My name
then I'm installing the spring, which we made on a mantle on the lathe. And now I'm going to insert the mantle with the spring, tighten around it, and then I'm going to unhook the end of the spring from the slot, and it's going to expand into the inside wall, and then I can remove the mantle. So, let's see how this goes. That side too. Now JJ is having an attempt. He has smaller hands. Can you reach it at least?
I think so. I mean, I can reach it by my hand.
Yeah, pull it. You got it?
Is this the side with the slot? Or like with the,
With the slot.
Okay.
It's with the slot.
Just the slot? What if like we pull it? Like you pull
So there are two loops in this experiment, the hot water loop and the cold water loop. The hot water loop is a closed loop, while the cold water loop is one that's open and starts from the sink and ends with the drain. So the hot water loop starts with this water reservoir over here, and the water from this reservoir is drawn in by the pump, goes up here through this water filter, and then through the hot water flow meter over here. This is an adjustable flow meter where flow can be changed based on the conditions that we want. And after the flow meter, it goes through this inline heater, over here, past these valves, and into the hot water inlet at the top of the heat exchanger. From the top of the heat exchanger, it creates a film in the heat exchanger, in the copper pipe, goes down here and back into the water reservoir, and then gets drawn in by the pump again, and that's the closed loop. Now walking through the cold water loop, we have the inlet which comes in from the sink. This is the inlet to the house from the city. It goes here to the cold water flow meter. Now once it goes to the cold water flow meter, it goes past a couple of valves into the cold water inlet on this side, and then it rises up in a helix around the heat exchanger to the top here. And here it goes to the drain. There were 3 tests that were conducted with this heat exchanger. One with the swirler at the top of the heat exchanger, another with the spring in the heat exchanger, and a third test with the swirler and the heat exchanger used together. Temperature was measured at 4 different spots. Hot water inlet is over here just before the hot water inlet of the heat exchanger. The hot water outlet is at the bottom of the heat exchanger over here. The cold water inlet is over here just before the cold water inlet to the heat exchanger. And the cold water outlet is just before the drain here. For all data collection, temperature was measured until steady state values were reached. Once steady state was reached, the average of the final 5 temperature values was taken to be used in the calculations. In each test there were 5 points of data, and each point of data corresponds to a different flow rate. So for the 5 points of data, the flow rates were 12, 10, 8, 6, and 4 liters per minute. And at each flow rate, steady state temperature values were found to get effectiveness and NTU, which were then plotted.
In conclusion, we found that the swirler on its own increased the effectiveness by more than either of the other cases, the spring on its own or the swirler plus the spring. Although the swirler still had lower effectiveness than the base case. It wasn't by much, so we can assume from this that the water splashing tangentially as opposed to just coming off the disc doesn't really make much of a difference. In the case of the spring, there was a larger difference in the hot water inlet to outlet than there was between the cold water inlet to outlet. This is probably because the spring was actually sapping some of the heat from the system, causing it to decrease in effectiveness. And so furthermore, we recommend that a spring or a swirler are not the best solutions for a gravity film heat exchanger. The traditional disc causing water to run off in a film works just fine.
It's working. It's working.